So in the last video, we looked at a set of rules to assign oxidation states, and unfortunately the rules are incomplete, and some books give you a much better set of rules than others. However, after a while you start to ask yourself, do I really want to learn 12 different rules to get the answer? And sometimes the answer is, yeah, it's actually easier, you should do it. And sometimes people are lazy, right? Or they're like, well, maybe there's another way to do it. And another way to do it is to actually do it using this method. So for instance, if you have a Lewis structure, and in a Lewis structure, you've got two atoms bonded together with a single bond. Okay, should put those lone pairs in. We can assign oxidation states by taking the electrons in the bond and assigning them to the more electronegative atom. So for instance, the electron pairs that are shared are assigned to the more electronegative atoms. And remember, your more electronegative atoms tend to lie in the top right corner of your periodic table. So you've got fluorine all the way up here. So typically as you go to the right and you go to the top, atoms get more electronegative. All right, so that is the assignment process. So now what's the point of doing this? Well, all you got to do now is draw a box around each atom and just look to see whether that atom has gained or lost valence electrons compared to the single atom by itself. So let's go ahead and look at a real molecule. So let's look at something like HF. So HF has a Lewis structure like this. Those electrons that are in the bond are assigned to the more electronegative atom, so that is the fluorine. And so we can imagine now drawing boxes around them. We ask ourselves, how many electrons did they originally have? We just look at the group. So hydrogen's in group 1, fluorine is in group 7. And now we ask ourselves, how many electrons do we have around it? So hydrogen has 0. Fluorine has 8. And so the oxidation state, or the oxidation number, okay, just represents that difference. So for in the case of hydrogen, it has 0 electrons assigned to it, but it originally had 1. So it has lost 1 electron, so it has a charge of +1, and which charge we call the oxidation number. So it's hypothetical because the electrons are pulled towards the more electronegative atom. In reality, they're not completely pulled off, but we're imagining this extreme where every single bond is purely ionic. In the case of fluorine, it started with 7, and now it's got 8, so it's gained 1 electron. So in terms of a charge, it has a hypothetical charge of -1, and the oxidation number then would be written as -1, like so. So if you remember before, when we did formal charges, okay, we actually shared the electrons equally. And this gives us the sort of the limit that everything is pure covalent. So in oxidation states or oxidation numbers, the electrons aren't shared equally, they go to the more electronegative atoms. Okay, so let's look at a fairly complicated molecule here now. So I'm not even sure if this molecule exists, but I'm going to go ahead and draw out a Lewis structure for it. And actually, I'm pretty sure this molecule actually exists. So here we go. This actually is a I think peroxyacetic acid, and we might assign oxidation numbers to every atom in this molecule. Now we could start out with the rules. We could just write a formula and say it's C2H4O3, and actually I'm not even sure the rules would give us the right answer, so I'm not even going to apply those. Instead we can look at the electrons in the bond and we can assign them to the more electronegative atom. Carbon is just a smidge more electronegative than hydrogen. Okay, so it gets all of them. And look at a carbon-carbon bond. Well, they have to be assigned half and half. So since they've got equal electronegativities, then they each get 1 apiece. Okay, and let's have a look at the other electrons. So the electrons between carbon and oxygen, well, they both go to the more electronegative atom here. And a double bond has got 4 pairs, so they both go like so. So we can draw the assignment in. It's kind of fun, isn't it? Oops, sorry. Oxygen's more electronegative, so I need to scrub that line. Yep, there we go. And here's the thing about peroxides. Peroxides have that oxygen-oxygen single bond, and the reason that there's that exception, and most molecules have a peroxide group, and the oxygens have an oxidation number of -1, is that normally oxygen always wins. It normally always pulls electrons off of other things, but if it's paired against itself, clearly it's a tie. Whereas here on the right-hand side, the oxygen and the hydrogen, the electrons go to the more electronegative oxygen. So now if we go ahead and we calculate the oxidation numbers or the oxidation states, All we got to do is say hydrogen started with 1 electron. Why is that? Hydrogen is in group 1A. So they have 1 valence electron in their Lewis dot structure. Over here, we can see that the hydrogens have no electrons at all. So they've lost 1 electron. So they have a hypothetical charge, an oxidation number of positive 1. If we look at carbon, carbon is in group 4A. So it starts off with 4 valence electrons. So if we look up here, we can see carbon's got 1, 2, 3, 4, 5, 6, 7. So it's got 3 more than it started. So it has a oxidation number of -3. If we look at the carbon next to it, we can see it's only got 1 poor little electron around it. So if it started with 4 and now it's only got 1, it has lost 3. So it has an oxidation number of +3 and so on. So the oxygen is in group 6. So it would have 6 valence electrons to begin with. Up here we can see it's got 1, 2, 3, 4, 5, 6, 7, 8. It's gained all of them, so it's got 2 more. So it has an oxidation number of -2. So most of the time oxygen has an oxidation number of -2 because it's capable of pulling all the electrons away from other atoms. The only one it can't is fluorine. And of course, if it's oxygen versus oxygen, it's a tie. So let's have a look here. Oxygen pulls all the electrons away from carbon, but it can only pull one of the 2 away from the other oxygen. So it's got 7, it started with 6, so it's gained 1 electron. Its oxidation number is -1. And we can do the same thing for the oxygen next to it. It is -1, and the hydrogen at the end is +1. We can sometimes check our work by remembering that the sum of all the oxidation states is the charge. So since this molecule didn't have a charge next to it, we would expect it all to add to 0. So 3 and 3 is 0, +1, +2, +3, -2 is +1, -1 is 0, -1, +1 gives us 0. So they all add up to 0, so everything is good. So that's another way we can do oxidation states. So you have to ask yourself, do I want to draw a Lewis structure for the molecule and do it this way? And if you do, the rate determinant step is probably constructing the Lewis structure, but figuring out the oxidation state is pretty easy. The other thing is the rules, once you memorize them, they're very fast and easy to apply. You can go through, 20 of these examples in a minute, whereas if you write a Lewis structure and partition them this way, it can easily take you a couple of minutes to do each one. So you have to decide, is it better to learn the rules, or is it better to learn where the rules come from? And I'll leave that one up to you.